The next talk is about secret sharing for high slices by Amos Bemel, Oriel Faras, Or Lasri, and Oded Neal. And Oded is giving the talk.
Hi, thanks for introduction. And as said, we'll be talking about secret sharing for high slices. This is a joint work with Amos, Oriel, and Or. And we've already heard the definitions for secret sharing, and this will be the finite case where n is set in advance and not the infinite one that Bar just talked about. So we have a dealer that holds a secret, it's randomized, and it wants to share it to n parties. So to do it, it sends one message to each of the parties, we call it a share, and we want to define in advance which coalitions between these parties will be authorized and will be able to recover the secret, and which will learn nothing about the secret. And we will call the list of these authorized coalitions an access structure. And the natural complexity measure for secret sharing is what is the best share size in which we can realize any access structure. Given such a list of authorized coalition, can we realize it efficiently with small shares? And even if we assume that we only deal with one-bit secrets, then some access structures are known to be very cheap, while others we don't know actually too much about them. So for simple access structure, say the one threshold, if we just want every party to be authorized on its own, we can just give it the secret and it will be a secret sharing scheme with one-bit shares. We also know that the classical Shamir scheme, where the threshold is T, where every coalition of size T is authorized, has log n bit shares, and there are other constructions based on representation of these access structures or as formulas or monotone span programs, where the share size will also be small. But the general upper bounds for worst case functions, for all functions, are not that great. It took a long line of work to get to this bound that applies to all access structures, which is 3/2 to the n, while the best lower bound known for an explicit function, or for any function actually, is of shares of size n over log n. So we have a huge gap here, and we don't know where the truth lies in between. And so two natural open problems given this state of the world right now is first, can we improve the share size for general access structures, or what is the real quantity there? And are there other natural families of access structures for which we can have secret sharing with small shares? So it turns out that in the center of both these questions, there is one particular family of access structures that is interesting to study. And that is the slice access structures that were also mentioned in the previous talk, in which a k-slice access structure satisfies that a coalition of size above k will be authorized, below k will be unauthorized, and coalition of size k can be either authorized or unauthorized. And we can see it visually, like with this axis between 1 and n representing the size of the set. So small sets will be marked in red because they are unauthorized, and approved sets will be marked in green. We have in the middle, the picture is a bit wider in this shape because there are many more sets of middle size and of small or large sizes. And in size K, we will mark by yellow, meaning that they may be either authorized or not. And in fact, this is a very large family. It will be interesting to realize it with small shares, because for every k, there are exactly 2 to the n choose k different slice functions. One of them is the k threshold one, for which Shamir applies. And as I hinted before, it turns out that all known upper bounds for general secret sharing, there are not the naive one of 2 to the n that went below it, are based on first realizing slice access structure very efficiently and then composing them together in some sophisticated ways. So this is the reason why they interest us. And besides that, they have other applications like attribute-based encryption, symmetric peer schemes, and even evolving secret sharing, as we have just seen. And so what is the state of the art for these slice access structures? So they have been studying by quite a few works. I don't mention all of them because even mentioning only this has a few complicated expressions. I will just say that one scheme on the right there is a naive one, and the other one is more complex. And I will focus, though, on two specific regimes. And one of them is when k is very small, say a constant. And then if we plug it into these schemes written there, we get a share size that is sublinear in n. But if we look at the high regime, where it's an n minus k slice where k is constant, then we get a polynomial upper bound on the share size by the naive scheme there on the right. And even if we look in a slightly higher regime, when k is logarithmic in n, we get n to the log n for very low slices, and n to the log n for very high slices. And this is actually the regime where k is equal to log n that is applicable in the construction of general access structures, because this is also an important regime. And we have this asymmetry here, and we ask whether we can improve it, or is it, does it have to be there? And can improving it help us to realize other families of access structures? So now getting to our results. So we indeed managed to improve the state of the art for high slices, and we realize them with this share size kn times 2 to the square root of k log n, which is at most n times more than the best share sizes for the low slices, so there's only a small gap there now. And this indeed enables us to realize much larger families of access structures more efficiently than known before, specifically multi-slices and also hypergraphs. But multi-slices are the thing that with the picture over there, where I will not define it formally, but we have degrees of freedom to more sizes of sets in between the zeros and the ones. And this is a first step in a plan laid out in previous papers to improve the share size of general access structures. There are more steps remaining, which we hope to tackle someday. And in addition, we also managed to realize high slices in the computational settings, in which privacy only holds against bounded adversaries, and so it's not information theoretic anymore, and therefore we can get even smaller shares based on the existence of one-way function. And perhaps surprisingly, here the schemes that we get in the end are more efficient than for the low slices. Somehow the techniques used in the computational version are more tailored for high slices than for low ones. But I will only have time to talk about one of these results, so I will talk about the first one. And even within it, I will only mention one simple scheme that we discuss in the paper. There is a more complicated one, but the simple one holds some of the key ideas that help us to improve the share size. So let's say now that we want to realize this access structure A. It's an n minus k slice. We have a secret S. So in this scheme, we start by defining a k-slice access structure B that is defined according to the access structure we want to realize A, in a way that sets will be authorized under B if the size is K, only if and only if their complement is authorized under A. So pictorially, say we have this access structure here, and X is an interesting set of size n minus K. Then under B, this set X bar will be authorized if and only if the set X is authorized under A. And now we only have two simple steps. The first one is sharing our secret according to B. In a black box way, we will use a secret sharing scheme for B. And then we take every share from the first step, let's say the share ST of the Tth player, and we reshare it with an n minus k out of n minus y threshold scheme. So we share it to n minus 1 shares, from which every set of size n minus k of shares will be able to recover the original ST secret, and we share it to all parties except for the Tth party. So we first share according to B, we get a share S1, we share it to all parties in the access structure A except for the first one. We do the same for the second share and the third, etc. And the correctness should be somewhat clear because the X parties can recover each of the shares of the X bar parties of the access structure B. It has exactly n minus k shares, and it's an n minus k threshold. And privacy can be implied for similar reasons. First, correctness is implied because these shares of X bar in B you can recover the secret from them because X bar is authorized under B because X is authorized under A. That's how B is defined. And the same works for privacy. If X should be an unauthorized coalition, then X bar should be unauthorized under B. The shares of X bar will tell you nothing about the secret, and the parties of X will not get any other share besides the one of X bar. So this means that, in fact, we have this black box construction, and whenever we have secret sharing schemes for k slices of size T of n, we'll get only a blow up of n to the schemes for n minus k slices. And this also has connection to questions about duality and secret sharing. I will also not define it formally, but dual access structures are ones when we take an access structure and flip it over and replace reds with greens. So k slices and n minus k slices are in fact dual access structures. And it's an open question, what should be the relation between share sizes of these access structures? And here we show that for slices, it is bounded by n. So that kind of concludes what we did. And for open questions, of course, we would like to somehow take this and realize general access structures more efficiently. And we also ask whether we can realize other access structures based on one-way function in computational schemes more efficiently, besides not only slices, maybe multi-slices or weighted threshold functions as mentioned in other talks. And we have this question about duality and secret sharing and what the gaps, the correct gaps there should be. And this is it. Thank you for listening.
Any questions?
Can I know what do we know about lower bounds for slice functions? Like anything we know about?
They're quite poor. It's logarithmic in n are for every share, similar to thresholds. We don't have, if I'm not mistaken, any better lower bounds for slices than for thresholds.
They're the same?
Yeah.
Thank you.
Any other questions? So maybe I ask one more question. I find it very interesting that for in the computation setting, you said high slice is easier than low slice. Mm-hmm. Is there a succinct way to give some intuition why that's the case, or maybe it's too involved?
There should be, yeah. So imagine in the classical Shamir scheme.
Okay.
Let's say we want to realize a slice k, so we sample a random polynomial where only about k of the coefficients in the polynomial are randomized and uncorrelated, like uniform random elements in the field, and the other had to be correlated with them. And in n minus k slices, the amount of uniformly random elements will be much larger, because the degree of the polynomial will be much higher. And then if we will be able to replace all of these uniformly random elements with a seed over PRG. And you replace more elements in the shares with seeds of a PRG, which are more efficient. And some of the schemes here are based on applying many high threshold functions like this, and you are able to save in the amortization of all of them because of that.
Any more questions? Or okay, if not, let's thank the speaker again.